My name is DiGiacomo. I'm the Senior Director of the Energy Management Programs and Business Continuity for the SCTE. I've been with SCTE for about 20 years, and I'm happy to be here and welcome to Powering IoT. And today we have Joe Rodolico from Comcast, and he will talk about how IoT energy consumption can be reduced and how we want to have a good strategy for batteries and managing the sensor experience in the various IoT devices that we will be deploying on our networks. And then after that, Patricio Latini, right? Did I get that right, Patricio?
Yeah.
Very good. We'll talk about low power WAN and IoT native protocols running over the unlicensed spectrum. So you see there's two very distinct presentations that we'll be having this morning. So I'm looking forward to hearing both of their presentations. Their papers have been shared to the website resource site. So I encourage you to download those along with the other presentations that were packaged for all of the other Expo workshops. So without further delay, I want to turn it over to Mr. Joe Rodolico.
Good morning. My name is Joe Rodolico from Comcast. I am a principal engineer at Comcast, hardware engineer. I've been in the cable industry since '83, which pretty much dates me, but I have been doing software and hardware in the industry. Basically, I joined Comcast 5 years ago and was given the Xfinity Home program to develop sensors and touchscreens with vendors. And in that process, I needed to gain the experience in choosing batteries for projects, which this presentation will discuss. And we'll go over the environmental impacts of batteries and the design of batteries, handling, procurement, and other such features. This page down. So the big thing about batteries environmental is when you have your products built overseas and they're shipped to the US, you ask the vendors, where are my products on the ship? Are they on the top baking and my batteries are depleting in my products, or are they in the bottom hold of the ship where they're supposed to be? A lot of vendors don't know how to answer that question, so you have to put that in your contracts. And when the batteries or the battery devices, or sensors come into warehouses, they need to be air conditioned, right? And humidity controlled also, because humidity is a parasitic effect on batteries. You can lose minute power from that. And then when the batteries devices or sensors or anybody's sensors or batteries go into the homes, you got to be cognizant of the temperature in the homes. Temperature in the home, obviously everybody keeps their home with a certain temperature range, but in reality, heating systems fail, air conditioning sensors fail. But these devices still need to work, so you have to design for those temperature extremes. And then you have the curious consumers who like to take the sensor and move them to a garage or a mailbox. So you have to accommodate that, you have to be cognizant of it. So this slide is very busy, and just like the home, with a lot of Wi-Fi, Zigbee, Z-Wave, Bluetooth, everything flying around. You have to be, everybody talks about battery life. Battery life, you have to take that into consideration of the battery devices versus other devices that are plugged in. One of the things is actually looking at the system. You can look at it on all modern systems have a monitoring system. We can look at the battery and look at the receive level on the battery, how it's actually, the signaling is going. And if it's not going well, say the bedroom in the upper bedroom, which is my daughter's bedroom, and other people's bedroom, the far bedroom in the house always usually has an issue. You put a repeater in if you have to. And that way, that battery will live fine. You just have to be cognizant of all these systems. Putting a metal cabinet in front of a door window sensor is not a good idea. Moving things around the house to orient it and just be understanding the other systems in the house is key. That's the next one. So let's talk about batteries. So a general battery, this could be a AA battery, this could be a lithium battery, CR2, whatever the batteries are. All batteries have internal resistors in them. Internal resistance. Basically, it's like a little resistor inside the battery. They all come with it. It comes in different ratings depending on the manufacturing. But the key about this internal resistance is the higher it is, the less battery performance you're going to get. So you want to choose batteries that are tested with low internal resistance. Well, it's not that you want to have the vendor test a whole series of batteries to make sure these batteries actually are under a certain rating so you are getting good batteries. And it's actually a mark of quality of manufacturing if they can hold to a certain level for internal resistance. This is an interesting chart showing lithium and alkaline batteries. Pretty much for remote sensors in the home, for sensors in the home, this is pretty much you're going to use. You're going to be using either AA alkaline batteries, or you're going to be using lithium batteries, which are AA or CR2, CR123, coin cells, whatever they are. If you look at the lithium batteries, they perform very well. They hold their voltage pretty well towards the end of the life. If you look at the alkalines on the right-hand side, they seem to slope down a lot faster. Those batteries, that's just typical of the chemistry of the batteries. But in this chart, you see the blue line, the underlining blue line. On the left-hand side, the blue line is internal resistance. You see it's pretty constant on a lithium battery. It then turns up towards the end. On the alkaline battery, you can see it's inversely proportional to the battery. The internal resistance actually goes up as the battery ages. So that's something you want to look at, and when you write your test plans, how these batteries perform, voltage-wise and internal resistance-wise. So you can actually buy batteries with advanced batteries, they call it a little more costly, with different chemistries, so you get extended battery life. But that's only in the domain of high temperature batteries. Here there's a battery. You can see that on the left-hand side, you can see the standard 2450 drops off over time, but the reformulated one in high heat will go further. Well, but the interesting thing about this, you say, great, this is what I want for sensors. Well, the challenge for batteries and the challenge for sensors is extreme cold, not extreme heat. Even though heat does fade the life of the batteries, the extreme cold, the operation, the capacity available at extreme cold is something that is more detrimental to batteries. The battery industry, as I'm trying to educate them, needs to reformulate the batteries for cold temperature also. But we test for batteries for cold temperature, and we make sure we get good capacity batteries. So batteries, all batteries have the alkalines and the AA's. They have seals. They have battery seals, and they actually have battery vents. If you see at the tip of the battery, there's holes in the battery on the corners. So that, as the battery's discharged, it lets off a little minute details of gas. It has to. That's what it is. The battery vents a little bit. So off to the side, and an experiment that was on the internet that I didn't believe it actually worked. If you take an alkaline battery, you take two fully charged alkaline batteries, and you deplete one, and you bounce them on the table, the battery that is depleted will bounce because it has gas in it. The one that doesn't will fall down. I didn't believe it would work, but it actually did work when we did the experiment. I don't recommend that for checking battery levels, okay? But if you're bored out of your mind, great thing to do. So the important thing about batteries is that contributes to battery life is actually the seal in the battery. So when you buy batteries today for your sensors, they'll either have a 5 to 7 year life, or actually a 3 to 7 year life, or 10 year life. And the difference really is based on how the seal was constructed. Is it just a two-piece seal which gives you a lower life, or is it a two-piece seal in a gasket which gives you that 10 years? And what you want is, for all your sensors, you want the 10-year battery life. You want the better seal, obviously. And it's not really, to me, it's not really more money. It's just getting the vendors who offer this. And that's where you want to go. So batteries, especially lithium batteries, so let's use the lithium AA, for example, or a CR2 or CR123 batteries. They should have PTC protection in it. They're required to have, if you're going to deploy a sensor, you want PTC protection in it. That protection is basically a fuse. If the battery's shorted externally, the battery will not put out any more power because the PTC fuse will actually heat up, open up, and it won't put power out to safety. Vendors do sell batteries without PTC fuses. You really do not want to put them in the field because you have a level of protection you're missing. You want that level of protection. So go back here. So what people do with devices, smoke detectors, remote controls, any company's devices, is they mix batteries, which is not a good thing. You don't want to mix batteries for two reasons. You may cause batteries to leak, as in this picture, but also what happens if you, and when I was a kid, I did the same thing. I went in a drawer, I put the old battery in with the new battery, and it worked. Well, what happened was the new battery was actually charging the old battery and doing equilibrium. Not a good thing to do. People do it. We recommend always replace with new batteries and with good batteries. Date codes, let me just cover that before I go to the next slide. The industry used to mark on the battery the date it was manufactured. Now they mark the date it actually expires. They'll say good by 2022. And you're saying, well, I got 2 years, 3 years with this battery. This is a good battery. No, that battery was manufactured in 2012. It's a 10-year life. So you have to almost back calculate when you look at a battery. So you have to think 10 years when you look at batteries, when you look at the battery life. When we put batteries in the sensors in the factory, we demand they be no more than 3 months old. So I know when the battery gets here, it's a fresh battery. So you may say, I'm doing a new design, I'll just get a brand name battery. Brand name battery is not indicative of a good battery. Every battery manufacturer can have a battery they buy either from another party and they put under their own jacket name, or they use a factory that is not a great quality factory. So what you want to do is you want to actually, in our respect, do our own testing, which we do. Get recommendations, and we'll go into that later. But in here, some people will say, well, I'm going to buy these batteries off the internet and I'm going to test them. Well, you don't know if it's sitting in a warehouse somewhere for 5 years baking its brains out. When you get it, the life is bad. I've gotten batteries in from the warehouses, and the big companies online I've ordered from, reputable companies, and some tested good, some tested bad. I gave that up. I go right to the manufacturer. I get my samples from the manufacturer and make sure I get good batteries with good date codes. I don't get them online anymore. But here's an example of batteries online. There's 3 batteries here that are all Panasonic. They're all 2450, they're all, what are these, 2032s batteries, right? Well, 2 of these are actually counterfeit batteries that you can buy online today at your major website. The one that delivers in 2 days or 1 day. You can have that imitation battery if you want. The one in the blue on the left is the original. Okay, the other 2 are counterfeit batteries. And not to pick on this manufacturer, they copy all manufacturers. They're all copied.
About halfway.
I'm sorry, okay, good. I gotta move then. So, battery packs. We're a little bit into talk about rechargeable battery packs, because I had to do rechargeable projects also. So you have the soft battery packs that you never want the customers to touch. You want to put a plastic case around it, like the old cell phones. You replace the battery with a plastic shell. So if the battery swells, obviously that's not a good thing. You want to avoid that. There's reasons why that happens, and they swell because of either bad manufacturing, bad construction. That's why you want to go to have the battery sent to a battery teardown house and inspected and x-rayed for production. So I'm going to show you, who doesn't have a cell phone here? We all have cell phones, right? So let me show you what happened. Let me show you what's in your pocket, if this works. Can I do the video here? I can't do the video. There it is right here. Okay, the video is running. So this is what happens when you take a screwdriver through your cell phone and stab your cell phone, okay? Not that you want to do this, right? This is what you're carrying in your pocket. Oh, a little bit of smoke. We're not done yet. That's what you got in your pocket, okay? That's why it's essential to test and validate that manufacturer, visit their factory, have that battery torn down and make sure it's made right. And then make sure they're not building on cardboard tables outside in the open air. Okay. Recycling, when your batteries, I'll move faster. Recycling your batteries, when you recycle your batteries, you say, oh, well, my vendor's recycling the batteries. You got to make sure they're not taken to a landfill, because batteries can be recycled. Some of the content can be reused for batteries. Some can be used for like lithium grease. You just have to be a little more assertive with the vendors. So let's go into energy harvesting. So energy harvesting is interesting. Everybody talks about it. You know, you have windmills, you know, you have wind, rain, you have all sorts of vibration, ocean currents, induction, light, all sources of energy you may be able to tap to, you know, extend your battery life, an IoT sensor. What not wind, obviously, but light is one subject. So I've identified in my studies like 3 types of mode. This hybrid mode, where the battery will put out milliamps for a sensor. That's pretty obvious. But energy harvesting, if I can find one that can do milliamps, then great. I can switch between the battery and the energy harvesting device to help that battery extend the battery life. Then the other mode I call sys mode. The battery, obviously the milliamps, but the energy harvesting is putting out microamps or microwatts. It's not putting out that much power. It could trickle charge my battery and extend my battery life. That's something good. That'd get me to the 10 years, right? I'm saying 10 years because we talked about the seal life. That's something we need to work with the vendors to extend the seal life. Then standalone, if you had a really good energy harvesting mode, if you're out in the sun and you have a solar cell that maybe has a super cap, you could just do an energy harvesting with that. So what's happening now in the industry for energy harvesting? Well, energy harvesting, the available power per energy harvesting techniques is slowly going up. The electronic circuits, the ZigBee, Z-Wave, whatever, the Wi-Fi SoCs, their power is starting to go down for the same functionality. And battery capacity is slowly going up. So the confluence is getting better, even better for battery life as we go on. So here's some battery capacities for IoT. You AA, CR12, coin cells for some legacy devices, that's happened. We use, and other people use, consumer replaceable batteries. You go around all the stores, make sure they have them, and it's consumer replaceable and available. So we have some energy harvesting techniques, so mechanical or RF or solar or temperature differential we want to go over and cover here in the next slide. So this is interesting. This exists today. It's a light switch that when you push the button, it sends a signal. It's basically your mechanical finger action, pushing on a light switch sends a short message. It doesn't listen, it just sends a message as lights on or off. In the middle, you have a solar cell that's out there, manufactured. It has a battery in it for, if it's by a window, it's a door window sensor, but if you draw the curtains over it, it still has a battery to work. And you have your solar calculator, which we have today. And here's some advanced energy harvesting, that there's these nano antennas, and there's these piezoelectric capacitors where piezoelectric, you can actually, it's like they need a demonstration of a flashlight with your hand from the heat, you can light an LED. But these are, you know, the microwatt devices. We need them to improve over time so we get more power for energy harvesting, but they're very interesting. We keep our eye on this. So in summary, you know, battery technologies, take a step back, the industry is just for batteries. The battery vendors themselves are basically, in my opinion, they're making batteries for flashlights, not for sensors. And we have to educate them that they need to change their design so we can get more power to vendors. I'm already talking to a vendor that can increase the common batteries by 30% to have one battery. And that looks good for energy, good for that. Energy harvesting, making sure your environmental, your batteries, that when you have them transported in the home, the conditions in the home, and just being cognizant of what you order and procure. Thank you very much.
Before I ask a question, I want to offer the opportunity for you to ask Joe a follow-on question to his presentation. Does anybody have a question for Joe? Okay, I did come ready. Oh, is there one?
Yeah, so you talked about, you know, the sensors that you talked about seem to be more mostly in
our other division that does the LoRa stuff is doing that, so I really can't speak to that, but yes, we have.
I was just wondering if you've had any experience with this battery vendors, for extreme temperatures like -40 degrees or something.
Yes, so what we do is when you buy a battery today, like the batteries in our sensors are rated at -20 to +70 or somewhere around there. Doesn't mean anything to me. I got to test it. Okay, so Minnesota. Let me answer your question another way. We'll answer it. In Minnesota, you can get down to -40 with single digits on a window frame. Right. So yes, the LoRa group, I'm working with them. I'm not really that familiar with what they're doing, but yes. We do work. We're aware of the extreme temperatures.
So ultimately, you have your own thermal chamber and that sort of thing. How do you do this temperature range testing?
Temperature range testing. I wrote my own confidential test plan that I share with the industry. So you have a good question, right? Because when I interviewed a couple of battery vendors, I said, "Show me your plant flow in construction, how you build a battery." And in the end, they said, "We check the voltage and we send it out." Right? So you have to do your own testing. You cannot trust the battery vendors, I'm sorry. Even though that battery's rated, that capacity at cold could be much lower than you have. I am speccing newer batteries now to have twice the capacity at cold than our newer batteries that are good to improve battery life. You have to do your own testing per vendor.
Any other questions for Joe? I have maybe 1 or 2 minutes left reserved for him before I turn over to Patricio. Okay, Joe, I have one for you. So what kind of advances on battery technology do you see coming down the road in maybe the next 2 or 3 years? Anything of note beyond, of course, traditional lithium ion?
The capacities are slowly increasing. What I am seeing is I'll put it out there, typically they do a spiral round battery when they do the battery designs. It's been known in the industry, it's called a bobbin type battery. If you do a bobbin type, you can increase the capacity by 30%. You drop the discharge to around maybe 100 milliamps, which is perfect for a sensor. So the battery guys need to get out of the flashlight world and into the sensor world. So that's what I'm driving right now. So I see 30% improvement in batteries for sensors coming down the road. I just got to drive the vendors that way.
Excellent, thank you. Let's give Joe a round of applause. As I'm teeing up Patricio's presentation here, I want to welcome him for his 20-minute discussion on protocols and LoRa. Patricio, take it away.
Thank you.
Yeah.
Okay, good morning. I'm going to talk today about an analysis I did about how to deploy LoRaWAN and some other low-power WAN IoT or using existing HFC or fiber infrastructure. So, basically I'm going to talk, the agenda would be the IoT goals in general, introduce LoRaWAN, and present some traffic and coverage models about LoRaWAN, compare that to HFC coverage models, and then talk a little comparison to LoRaWAN versus LTE and some different use cases of each of one. So, basically the idea of IoT is having communication in 3 axes. That is anytime communication at any place of anything. So basically, it's not just humans talking, browsing the internet or human-to-human communication. The important thing is now thing to things. So, and this needs to happen moving at daytime, during the night, and it can be, like we said, agricultural, can be outdoor with very extreme conditions, or can be indoor in a basement for a fire sensor. So basically, the idea of IoT is providing all these 3 axes of applications. The study is that there is a projection done from Ericsson in 2018 that the IoT is going to have a exponential growth in the quantity of devices. Today I'm going to focus about the wide area IoT. That is one of it's the one that expects to have a 30% year-over-year growth. from now up to 2022. So, and I think that it's the one that better applies for doing an overlay with an HFC network or a fiber network. So, talking about LoRaWAN, and very well aligned with the panel here, is the main consideration about LoRa is being really low power and having up to 10 years of autonomy in a really harsh conditions, like really cold or on environments where you cannot easily access to replace the battery. So the thing is that when you have a very wide area, you can have a strong penetration of devices, and there is an analysis that I have done later, that you can have like each light in the street with a sensor or a transmitter, and you can have a very dense or a very high number of devices in a certain area. So when you have a large number of sensors, there can be some bandwidth issues, but also the important thing to consider is that these sensors are really low bandwidth devices. So for instance, a light in the street is going to report you a single bit or byte, depends how you transmit, each 15 seconds or 45 seconds, depending the frequency of the light, but it's not something that you talk about kilobits per second. You are several orders of magnitude before. And also, one of the design things about LoRa is that you have a great range of links. You can have a link up to 100 miles or links up to 500 meters or yards. So the protocol needs to handle that. So how the LoRaWANs do that? Basically, it uses symbol spreading, and it has a very wide spectrum of spreading. So you can spread from when you transmit a symbol or a byte, that symbol is spread using a spreading code that is 2 times the spreading factor, and that can be range from 6 to really, let's say, close applications up to 500 yards, up to 12. When you use 12, you are transmitting a byte, and if that byte takes 100 milliseconds, or less, let's say 1 millisecond, it's going to take 4 seconds to transmit, because you are spreading that byte is spreading a time 4,000 times. So that gives to the protocol a lot of immunity to noise, but of course reduce the transmit bit rate of the total channel by a huge factor. So and that is reflected there. So you can have bit rate, total channel bit rate of 366 bits per second on the highest propagation factor, that is spreading factor 12, and you can have up to 48 kilobits per second, something that is a little more decent on a spreading factor of 6. But now I'm going to show you later in one of the next slides, what distance you need to be in each of the spreading factors. The other thing that LoRaWAN has is some, let's say, MAC level protection. So you not only have this spreading that is at the physical level, but also you have, like you have in DOCSIS and like every digital protocol almost, a forward error correction. So that forward error correction range from adding a single byte to adding a full 4 bytes, each 4 bytes that are transmit. So you have an efficiency ranging from 80% when you add a single byte of overhead to 50% where you transmit 4 bytes and then you add another 4 bytes of redundancy. So here I have made a little table that reflects for each of the different spreading factors and for each of the coding rates what will be the effective bit rate for a single 125 kilohertz channel. So you see that things, are in the tens of kilobits, 10 kilobits range for, really close application with not a noisy environment, to really low bit rates on very long spreading and a lot of and high error correction. Another factor that affects LoRaWAN particularly is that it uses Aloha as a transmission and contention method. Aloha is a protocol, that is uncontrolled and it's carrier sense. So when somebody when a transmitter needs to transmit, it senses a channel. If there is somebody transmitting, it waits, back off, and transmit when there is nobody transmitting. But there might be collision there, so there might be a back off. And there are a lot of papers about that, but in general, it has been studied that an Aloha channel has a maximum throughput available that is 18% of the total channel availability. So we had that to 11 kilobits per second, but really, because we are using Aloha, we can only reach 2,000 kilobits per second on a single channel. So we can see that all the bit rates get reduced by distance and by the nature of the protocol. So the main conclusion we can think here is that we need to be very careful planning on how big are our areas of service and how many sensors we are going to have in that area, because we can easily reach that very low numbers. Typically, the LoRa gateways that are on the market right now are 8-channel gateways. So now we are a little better because we can multiply that single channel number times 8. So we have a little better bits per second on the total channel. So here we have the figures, and the next step of the analysis is what all this mean in terms of coverage. So here you have what that means. So this is the equation for free space path loss that you have at 900 megahertz. In general, in most of the countries, like in the US and Latin America, is 900 megahertz for LoRa. In Europe, it's 860, so it's around the same frequency. So if we do this calculation and we take what is the SNR limit for each of the spreading symbols, you can see that the more you spread, you can go lower. You can be up to minus 20 dBs of SNR, and if you do your calculation of your maximum transmit level allowed by the FCC or by law, that is 14 dBs, and you calculate the free space path loss, you can see that we can have coverage up to 900 kilometers or 600 miles. In fact, the world record right now that was tested in the field was a transmission that was done at 700 kilometers. So somebody put a LoRa transmitter, send it in a balloon, and put a transmitter, because with the curvature of the Earth, you cannot do 700 in a single line, but they send the balloon, and we were able to almost demonstrate the maximum coverage. But that is not something that is relevant to us, but good to know. So the other thing is that free space loss is not the same than having the environment of a city, of a suburban or urban environment, where that is not free space. You have a concrete, you have buildings. So there are several models that have been done, especially for mobile transmission. So I have in my paper, I have put them on the analysis. So there is a model that is called HATA, that HATA did, but it was limited to gateways over 30 meters. This was an original analysis done for mobile towers, because on the macro cells, they are over 30 meters or 90 feet. So it is a good model, but it doesn't apply directly. And there is another model that evolved from that one, that is the low height antenna model. That is much better, because applied to antennas that are at the level of a typical sensor, that is 3 feet to 8 feet. So, and basically you have some constants in that model that is, the area type. They model that, you have an addition of 24 dBs if you are in a suburban environment and 5 dB more if you are in a urban environment with a lot of concrete buildings. And then you have some building attenuation because you have to consider if your sensor is indoor or outdoor. And if it is indoor, you have some constant for if it is concrete, that is like 17 dBs, but if you are in a suburban house that is wood and brick, of course it's less attenuation, so that's 5 dBs. And then you have some also shadowing effect. If you are in a very rural area, you don't have shadowing of the other buildings, but if you are in a, in a commercial building areas like, Wall Street or in New York, you are going to have a lot of shadowing from that building. So, if you put all that together, here I have put the curve of the propagation loss based, for instance, in this scenario, I said, we are in a, downtown here in New Orleans, you have dense urban, concrete buildings, and you put indoor sensors. So I put all that, I assume a height of the gateway at 9 feet, that would be, 30 feet, 9 meters, that would be a sensor put on a node, on an amplifier, and a gateway, and a height of the sensor like 1.5 meters, 4 feet, that would be somewhere in the home. And I put here the different constants that I mentioned before. So that means that, you can reach with the best profile, like, highest bandwidth, 750 feet, so not alone. And for the really low bandwidth, that would be 1,600 feet. So that are the lines, the green lines and the red lines. You see the dropout of the you have in the y-axis the dBs of path loss and the distance in meters. So you can, where the axes are cut, that is your coverage. I have done the same thing for another propagation model that is suburban, where you have houses and indoor sensors. Same thing here, you have a much better coverage. You have like 0.4 miles for the best profile and 0.9 miles for the, let's say, low bandwidth profile. And so the next thing is, you have an HFC network, node plus 0, fiber deep. So, in that network, and I have used some real life scenarios from a couple of operators that I cannot mention, but the HFC, you have typically in node plus 0 networks, you have cable runs that are, no more than 600 feet from where is the main node, and, and that can be even less, like 500 feet from the in a radial pattern. So in that scenario, you can put, what happens if you put a LoRa gateway on that node? And one important thing is why I want to put a LoRa gateway in a node, and it is, I have power there and I have a backhaul there. So I don't need to do anything weird, because one of the biggest constraints of LoRa, or any like wide area IoT protocol, is that the gateways, need to be outside or somewhere, and you need to provide backhaul and power. And in our node or amplifier, we have backhaul. We can be a DOCSIS connection and a modem, and we have power from the HFC. So in this scenario, we see that with 700 feet, we can serve, in a dense environment, all our stations with the best profile. Basically, if you have, in HFC networks that are, node plus 1 or node plus 2, same thing happens, because, we can have, coax runs up to 1,500 feet, and we are still in a good position, because we can serve, if we are in a dense environment, typically node plus 1, and sorry, my heading is not correct there, should be node plus 1, but typically node plus 1 or node plus 2 are in a very wide area, like rural or suburban scenarios. So you can still put your transmitter in the node, or you can use your amplifiers, and you will be still on the coverage of the gateway. So so the next thing is you can put an 8-channel gateway. An 8-channel gateway have a power consumption of below 5 watts. So that's something that regarding powering, the node can serve easily. Typically an HFC node range from 70 to 120 watts, and the DAA nodes are even more, 140 to 160. So really adding 5 watts to that envelope is not an issue. And here I have made an analysis of this is a paper there that says they have modeled how many you have in an urban environment like New York City, or a suburban like in Washington, how many homes per square mile, how many grocery stores, how many restaurants, how many road signs, traffic lights, and sensors. And if you divide that by the area, we talked about a cell radius or a gateway radius of 200 meters, or for urban, or 200 yards, and 500 yards for suburban. How many devices you have in that cell coverage, and that of course relates to how what bit rate you are going to have. And there is a model for each kind of device that for instance, a traffic light, like I mentioned, it has a byte per minute rate. A traffic sensor has 10 bytes per minute, and a road sign might have different rates, but that all that is modeled. So basically, you can know in advance what would be the bit rate for your area, and if your gateway is going to serve that well. So of course, I talk about doing backhauling of the gateway. Really, we were talking about 8-channel gateway doing 15 kilobits of throughput. So really, that is not an issue for a cable modem providing a 15 kilobit service. And the good thing is that you can take advantage of using like a warranty service on the DOCSIS level, like using UGS service. So the latency is the least, and you can have immediate delivery of the information without delays. Also, I have made a comparison. There are, there is also a range of other IoT technologies like LTE-based. So LTE-based, basically you put a SIM card on your IoT device. I see more the IoT-based, LTE-based IoT more for applications that don't require that low power. I see LoRa as the main app driver for like these 10 years of battery duration, because it's really low on battery consumption. So I see LoRa really good for like smart cities, like putting sensors on the lights or on the road signs, and like agricultural. But because LTE-based IoT is more about let's say where you have good coverage of your LTE network. So the new thing on LTE is the small cells. So I made an analysis on a city where we put three different small cells, and what would be the coverage of a small cell to serve that devices. So basically, it's also really well aligned, and these were HFC-based small cells, so put on a DOCSIS network. So as you can see, the cell radius has ranged from up to 200 meters, and that is also really well aligned with the same analysis I did before for LoRa. So really, one of the things is that LoRa and LTE-based IoT, they don't compete, they complement each other. So as a final conclusion, I want to mention that after my analysis, I found that HFC networks provide the right supporting infrastructure for IoT networks, and that is without a significant effort of, you don't have to do significant changes, and that, if vendors start to add, gateways on the nodes or the amplifier, that would be, something easy to implement. The coverage in that area is really well aligned of the location of that fiber nodes. And of course, doing that can provide to the MSOs extra revenue streams that, can allow them to provide this service and doing the investment, because, smart cities and this IoT service would be new revenue streams. So that's all from my side, so thank you.
Thank you, Patricio. So again, I want to offer opportunity to ask a question or two to Patricio. Otherwise, I did prepare one or two questions for him. Any questions from the audience first?
I have one.
Oh, Joe, go ahead.
So you mentioned it was only 5 watts on the node, the load, right? Have the cable, have the node providers confirmed that this is not an impact on the nodes?
Yes,
Okay.
yeah. That's one of the things I mentioned there is that, adding 5 watts to a node or amplifier, it's supported by the power supplies on the nodes, but also, on the power supplies that like the alphas, the one you have on the strand, and that can support without, any significant redesign.
Okay.
On the.
So that's been confirmed.
Yeah.
Thank you.
How would you deal with the interference between the HFC downstream and the 900 megahertz LoRa?
Well, that's a really good question, and based on the band that that where LoRa is, that is 915 megahertz. If you have a Docsis 3.1, you can avoid configuring the CMTS to skip that 2 or 3 subcarriers, because really it's going. If you use a 8-channel gateway, that would be around 1 megahertz of spectrum. So you can do a notch there on the Docsis 3.1 OFDM and avoid, let's say, bidirectional interference by the. I think that the interference from the cable is going to be more to the LoRa than the LoRa to the HFC, because it has a really long symbols, and you can see that a transmission can take up to 500 milliseconds. But Docsis 3.1 brings you the ability to make a notch there, and you're not going to lose a lot of bandwidth by notching there.
Good question. Another. The question was, what's the advantage of Docsis 3.1 versus 3.0? It's totally off topic, but do you want to address that?
No, well, I think that, there are, I think, several different angles to see that, but I think that on the 3.1 side, you can have the ability, like I mentioned, of avoid the bands that LoRa uses and avoid the interference. In Docsis 3.0, you will need to eliminate a complete 6 megahertz channel. So, it's a pretty important number of channels that you are going to lose, because it's 40 megabits. With Docsis 3.1, you can notch just the band of where you are using the LoRa spectrum. And that is not only for LoRa, it applies also to LTE or any, offending RF transmission that might give you problems on the spectrum.
Did that help? Excellent. Any others? I have one more for you if there are no other audience questions. Oh, yes.
Isn't it a bit risky to build an infrastructure-based wireless system in an unlicensed band? Like, you never really know what's going to happen.
Well, there is some risk there, of course, because it's unlicensed and you never know what is going to happen. But, you have also CBRS for the mobile. So I think that, this, at least LoRa and these, protocols are really well designed to tolerate interference and are really strong in order to handle that. And, of course, you can have people doing bad things and start interfering your LoRa band. But, I think that, with the proper enforcing, that shouldn't be a problem. But, of course, people can interfere in also your license band, so if they want. But, I think that, particularly in that band, you don't have a lot of other kind of devices because you have the 2.4 or the 5.8 bands where, you have a lot of people, using for Wi-Fi and even microwaves. But in this 900 megahertz, there is not a lot happening. So I think the risk is much less.
Time for one more. Well, you mentioned LTE and LoRa are complementary. Do you have a good use case for each? Why would you use one versus the other?
Yes, I think that what I have seen in the market and what I agree is that LoRa is more for areas where you want to put standalone sensors that you are not going to serve. You don't want to visit like every 2 or 3 years. There are the lights, the smart cities in general. It's a really good scenario, and also the agricultural and anything that is really unattended. And the IoT base, I think I see it more for like indoor applications, like alarm systems and even some kind of water pump monitoring and even like metering sensors that are more on the LTE side because you can have better powering. The meter has direct access to power, and I see more LoRa on the other side.
Very good. So with that, I'd like to thank both Joe and Patricio for their excellent presentations. Again, you can download their material, including the slides in PDF format, off of the distribution site. And also, Joe had written a paper that was published in the SCTE Journal of Energy Management a couple cycles back. And you can get all of those journals, including DVS, the Digital Video Subcommittee, and the other one is the NOS, the Network Operations Subcommittee Journal Archives, scte.org/journals. They're free to everybody, and please download and read those excellent submitted papers. So with that, thank you, Joe, thank you, Patricio, and thank you all for coming this morning.
Thank you.